Yeah, now we move to the control chart. Okay, so control chart basically is viewed as a visualization of our statistical approach or of our statistical approach. Okay, but the key essence showing here will be still exactly the same as we just mentioned. We're trying to monitoring two aspects of our of the quality. Okay, which we are related to first of all, the central point of the product and also the variability of the product. Okay, so both aspects are very important for us to improve the quality overall. Okay, now within the control chart, there are two very important things that we need to monitor or we need to basically calculate. Okay, we need to calculate. Okay, and which are called upper control limit and a lower control limit. Okay, now let's use a very simple, plot or a very simple figure to basically illustrate what is the control chart. What are the key elements within the control chart? Let's look at this plot. All right. Now you can clearly see that this will be the control chart. Okay, and the key elements showing here are UCL and LCL. These are the two things that we need to calculate within the control chart. Okay, I will talk about how to calculate UCL and LCL, just in a second. But before we even start to calculate, no matter UCL and LCL, okay, what it means for UCL and LCL. Okay, suppose you already know the value for UCL and LCL. What it represent for? UCL represents the upper control limit. LCL represents a lower control limit. Okay, so UCL basically is representing the upper limit that is acceptable within the quality management process, right? Very straightforward, right? And the LCL represents the lower control limit that is acceptable within this quality management. Okay, so if any of the, for example, if any of the dot, okay, is outside of this control chart, what it means? It means that, okay, when you monitor this process, okay, if any of dot is actually outside of this control chart or outside of no matter upper control limit or lower control limit, it indicates that your quality actually has some problem. Okay, you have to deal with it. You have to figure it out. Figure out the underlying reasoning. Okay, as much as possible, and try to make it, the variation within the upper control limit and lower control limit. Okay, that's our very important target that we want to reach during the quality management process. Okay, now suppose UCL is right here as a red line shown here, and the LCL is right here. Okay, if you look at this plot, okay, can you figure out some underlying reasoning by looking at this plot? At least from my perspective, all right, this plot actually is very normal. Okay, this fluctuation shows here is very normal. It doesn't actually send us very strong message that how this variation is changing, okay, during the whole fluctuation period. Okay, so that's why here, if the control chart is like this way, okay, maybe it means that basically the whole overall quality management here is still in control. Now let's look at some situations that do send us some strong message by looking at the control charts. Let's look at this one. Okay, if you look at this control chart, okay, if you look at the dot, all right, clearly every dots are basically within the range of UCL and LCL. That's good. All right, but you do find out that actually the variation shown here, all right, within your sample, different sample shown here, actually the variation here has a decreasing trend, right? It actually send you some message that actually, basically the sample characteristic, okay, represented by every dot is actually decreasing. Then you basically send you this message, and once you, for example, for an employee who is monitoring this whole process, after you look at this plot, you probably need to basically assess the performance. You have to do something in order to figure out the underlying reason. Okay, right now we're not talking about how to figure out the underlying reasoning. We're talking about the monitoring process. Okay, so this will be one case. Let's look at another case. in this specific situation, okay, at the beginning, you can see that basically the variation of the sample characteristic is, you see, this is quite normal, okay? But start from this dot, okay? The sample characteristic within this, this control chart, you see the variation decrease, the sample characteristic decreasing a lot and then increasing a lot. All right, so this type of the movement actually also sending some message to you. Okay, so you have to figure out the underlying reason if you meet this type of situation by looking at the control chart. Okay, how about this one? Okay, this one is very obvious, right? Because if you look at the variation of the sample characteristic, okay, you can clearly see that, okay, it's first decreasing and then increasing a lot. Even you see breaks the upper control limit, okay, and then decreasing and then still decreasing, even breaks the lower control limit. So if this type of the situation happens, okay, normally, okay, as the employee, if you monitor the whole process, you probably have to stop the production process immediately, okay, because definitely something is happening underneath the production process. You have to figure it out, okay? Otherwise, it may actually incur huge cost within the, no matter production process or the service process. Okay. Now let's continue. These are two types of the errors actually that will basically happen within the overall statistical process. I would not mainly focus on talking about or test these two different type of the error that will frequently occur within the whole statistical process. But at least you should know what is the key difference between type 1 error and type 2 error showing here. Okay, I may not actually ask you guys to calculate type 1 error, type 2 error within this course, but you need to conceptually know what is the key difference between type 1 error and the type 2 error. Actually, very simple, okay, to figure out the reasoning. Type 1 error, okay, type 1 error actually is representing the case that, okay, if you think, okay, you made a mistake, but actually you didn't. This actually represented type 1 error. Let me repeat it again. If you think you make a mistake, but you didn't in the reality, okay, in real situation, that is representing type 1 error. Oppositely, it will be type 2 error. What is type 2 error? If you think you didn't make a mistake, but actually you did, okay, but actually did, that's actually representing type 2 error, okay? So keep in mind what is the key difference here, okay? In type 1 error, if you think you make some mistake, but you didn't, that's type 1 error. For type 2 error, if you think you didn't make a mistake, but actually you make some mistake, okay? So that would be type 2 error. All right, now let's continue. Now, from now on, we actually we will start to talk about 4 different type of control charts, okay, within our quality management process, okay? You may wonder why we have 4 different type of control charts. Every single type of control chart is basically monitoring one specific characteristic of your sample, okay? One specific characteristic of your sample. We will talk about R charts, we'll talk about X bar charts, P bar charts, and also C chart, okay? Every single chart, first of all, every single chart is one type of control chart. It's monitoring one specific aspect or one specific characteristic of your quality, okay, within your sample. Now, before we even jump into the technical detail about every single chart, let me, first of all, illustrate the big picture of these 4 different charts. Actually, the underlying structure among these 4 different charts are very similar, okay? So I think if you can understand the key difference among these 4 different charts, okay, you already get at least half of the overall idea, okay, related to the control chart, okay? So first of all, okay, no matter which type of chart, no matter it's R chart, P bar chart, X bar chart, or C chart, okay, the key technique that we need to measure are basically just 2 simple things, okay? Actually, we already discussed about this by using the plot. What are the key 2 elements? Very simple. No matter it's within the R chart, X bar chart, C chart, or P bar chart, okay? The 2 key elements would be UCL and LCL. That's what I just mentioned, right? Upper control limit and lower control limit, okay? So the simple thing here, okay, you can imagine here, all right? So basically for this specific control chart, okay, it can be an R chart, it can be an X bar chart, it can be a C chart, it can be a P bar chart, okay? So it depends on what specific sample characteristic you are measuring right now, okay? But no matter which type of chart, you always need to calculate the corresponding UCL and LCL, okay? Related to how to calculate UCL and LCL, okay? I will talk about that in detail just in a second, all right, just in a second. But remember, no matter which type of chart, okay, you need to basically calculate the corresponding UCL and LCL. Of course, the equation to calculate UCL and LCL within every single chart is different, for sure, all right? But these two elements, okay, are exactly the same within different charts, okay? Now, the first question that we need to figure out before we start to calculate something related to different calculate no matter UCL and LCL in different charts is that what is the specific sample characteristic that every chart is measuring for? Okay, now we start from our chart. Actually, I already emphasized in red within the corresponding slides. R chart, what is R mean? R means range. Okay, R means range. R chart basically is monitoring how the range of the samples fluctuate during a production process. Okay, how the range of sample fluctuate during a production process. So the sample characteristic that our chart is measuring is what? Is basically the range of the sample. Okay, we will use specific example to illustrate, okay, how basically our chart is measuring the range of the samples fluctuate during a production process. Okay, but first let's look at some other chart, X bar chart. Okay, you guys all know what means by X bar, right? X bar means mean. Okay, then you can even imagine what X bar chart is measuring. X bar chart is measuring, basically is monitoring how the mean of the samples fluctuate during a production process. Okay, so basically the sample characteristic that X bar chart is monitoring is basically the mean of the sample, is sample mean, or basically sample mean. All right, so this is for X bar chart. Now let's directly jump to P bar chart. All right, what is P bar chart is monitoring? Very simple. Okay, what is P bar means? P actually represents the proportion. Okay, proportion. Okay, and the P bar chart specifically is monitoring how the fraction of the defective products fluctuate in the production process. Okay, so since P represents a proportion, all right, so basically that's why you see the sample characteristic that we are trying to monitor here, okay, is a fraction, or we can say it's a ratio. Okay, and more specifically, the fraction and the ratio we try to monitor here is basically the fraction of defective products within your sample, the defective products within a fraction of defective products within your sample. Okay, and we try to monitor how this specific sample characteristic fluctuates in the production process. Okay, now finally, C chart. What C chart means? Okay, we all know that, for example, if one product actually has multiple parts, okay, then the defective parts within one single product can be multiple, right? So basically it indicates that the defective parts with one product can be 1, can be 2, can be 0, of course, can be 1, can be 2, can be 3, okay? So C chart basically is monitoring how the number of defect parts per unit or per product fluctuate during the production process. Okay, so you can clearly see that basically for every single type of chart, okay, they have the corresponding, sample characteristic that they are trying to monitor in order to monitor the overall quality management. Okay, so the first thing, and I think one of the most important thing that you need to keep in mind before we start to even talk about, how to calculate the UCL, LCL, this kind of things. Okay, the most important thing is to first exactly understand what are the key essence of each chart. What are the key differences among different charts? Okay, what every chart is monitoring for. Okay, now after you understand the key differences among different charts, okay, then we can jump into the technical detail of every chart, because no matter is related to, let's say, start from the beginning, no matter it's related to R chart or X bar chart or P chart or C chart, right? It's basically, you're basically still trying to calculate those two key elements within every chart, right? So these two key elements within every chart is exactly the same, UCL and LCL. All right, UCL and LCL. But how to calculate UCL and LCL for every chart, the equation itself will be different. Okay, the equation itself will be different. Now, let's start from calculating UCL and LCL for our chart. Okay, as you can clearly see here. Okay, first of all, okay, you can clearly see here the common part, no matter whether UCL and LCL within our chart, is this R bar. What is R bar? R bar basically represents the average of the sample range. Okay, average of the sample range, because we will have different samples, okay, within this whole population. And for every sample, we will get a sample range, okay? And R bar represents the average of the sample range. Okay, you may get a little bit confused about the definition. We'll use a very clear example to illustrate this. Okay, just wait for a second. All right, now D3 and D4. You can clearly see that for D4, this is related to UCL, and D3 is related to LCL. Okay, basically these are the coefficients when we try to calculate corresponding UCL and LCL. Okay, and I can tell you guys that this is actually summarized within a statistical table. So if we, within the exam, if we ask you guys to calculate, UCL and LCL, okay, based on the table, then we will provide this table. And what you guys need to understand is how to appropriately use table to figure out, to guess the corresponding appropriate D3 and D4 within that table. That's good enough. Okay, that's good enough. Okay, now before we, start to, use the example to illustrate our chart, let's first look at X bar chart, because X bar chart actually is a little bit similar as our chart. All right, now if you look at X bar chart, okay, there are still two elements when we try to calculate no matter UCL for X bar chart and LCL for X bar chart. Okay, although the equation here is totally different from the R chart calculation. All right, and here the first element shown here, this is a X double bar. Okay, X double bar. We already know what is X bar, right? For example, if we have one sample, the X bar represents sample mean, of course. Okay, but what is X double bar? You can even imagine that, right? Since we already include multiple samples when we try to monitor the quality management, right? When we try to monitor quality management, so every sample actually includes a sample mean, right? So the X double bar actually represents the average of the sample mean. Okay, so every sample has a mean, but what is the average of the sample mean? That's actually represented by X double bar. Okay, X double bar, and still it has the R bar within this equation. Okay, and another thing is basically coefficient shown here, which is A2. A2 is also provided by the statistical table. As I said, if we use table to calculate, UCL and LCL within X bar chart, we will provide to you within exam. Okay, now let's use let's first look at this table, this statistical table. Very simple. Okay, this is actually very simple for us to use in order to figure out what is corresponding A2 and D3 and D4 for the corresponding X bar chart and R chart. Okay, let's look at this. So how we get the appropriate A2, D3, and D4 for when we calculate, no matter UCL and LCL for X bar chart and R chart. All right, so it's depending on the sample size. Okay, you know that. Okay, we may have multiple sample. Okay, when we try to monitor quality management. All right, but normally, okay, the number of the products within every sample will be exactly the same. What is the number for that? It's depending on the context. All right. So, for example, in this example one, okay, in this example one, you see that we collect 5 different samples. Okay, and look at this. How many observations within every sample? 4. All right, 4 observations is within every sample. So then, okay, the size of the sample should be 4 within that specific example. Okay, then you can clearly look at the corresponding row, and A2 will be 0.729, okay? And D3 will be 0, and D4 will be 2.282, okay? So at least by using this statistical table, we can, after we clarify what is N, okay? N here represents the sample size. Actually here, I really want to emphasize, okay? I found out that actually many students may a little bit confused about this M, meaning of M, okay? This actually represents number of the products within every sample, okay? It doesn't represent the, how many sample we have within this specific application, okay? What it means, what is the key difference here? In every sample, you have 4 observations, okay? So that's why here N equals 4, okay? But some students, they may actually incorrectly interpret as the number of samples. Then they may say, okay, we have 5 different samples. No, this is not what we are talking about, okay? For representing N, showing here, okay? N shows here represents the number of products within every sample, So keep that in mind, okay? So that's why N should be equals to 4 in this specific example. And the corresponding A2 and D3 and D4 can be easily get, okay? Now, let's jump into this example to fully illustrate how we get UCL and LCL for both R chart and X bar chart. Okay, now, as I said at the beginning, okay, I won't actually go through all the context here, but let's first directly look at this table, okay? This will be the information, at least for the first 5 columns, okay? First 5 columns, okay, this part. This can be viewed as information that is provided by the context, okay? And besides that, probably these are all the things that you probably need to calculate. But actually the underlying reasoning here is very simple. Let me help you guys illustrate. First of all, okay, R chart, as I said, R chart actually is monitoring what? The range of the sample, okay? The range of sample. X bar actually represents the mean of the sample, okay? It's monitoring the mean of the sample. So first, let's look at some measuring related to R chart, okay? So if we look at the sample 1, okay? If we look at sample 1, there are 4 different observations within sample 1, right? What is the range of this sample? How we calculate the range of sample? Okay, always keep in mind, very simple. If you calculate the range of sample, you just use the maximum value within this sample minus the minimum value of this sample, okay? Look at these 4 values. Which one is the maximum value? Very, very straightforward, right? 0.5027, this is the maximum one. What is the smallest one? This one, 0.5009. This is the smallest one. So you use 0.5027 minus 0.5009. You will get the corresponding result, C, which will be 0.0018. Very simple, all right? Always keep in mind, if you calculate the range of every sample, you use the maximum value minus the minimum value. That's it, very simple, all right? Now, you can follow this fashion to calculate the range for the second sample, the third sample, the fourth sample, and the last sample. That's it. So basically, if you calculate range for every sample, you just follow this way. But keep in mind, when we try to calculate the UCL and LCL within within R chart, we're not directly, we're not trying to get, R, but instead we're trying to get R bar. Okay, what is R bar? R bar is the average of the range of the sample. Average of the sample range, okay? What is the average of sample range? Actually, very easy. Here, okay, you can clearly see that for every sample, you already get the sample range. But what we need is the average of the sample range. Average of sample range, what you need to do? You basically just add all them up. All these 5 elements, all right? Add all them up, divide by how many? 5, because you have 5 sample range, right? You have 5 sample range. For every sample, you get a range. You have 5 sample range. So you add all them up, divide by 5, you will get the R bar, which is 0.0021. Okay, 0.0021. So, which is very, then the this whole process is very standard, right? Right now you already get R bar. Okay, R bar would be 0.0021. That's basically the numerical value that you need to plug into this equation. Okay, and what is the corresponding D4 and D3? Very simple. Since within this example, as I just mentioned, for every sample, okay, for every sample, you have 4 observations. Okay, you have 4 observations. So you get back to this table, look at the sample size, which is corresponding to 4, and then you look at D3 and D4. D3 is 0, D4 is 2.282. okay, you also plug into the specific equation, you get the corresponding UCL for R chart and LCL for R chart. That's it. Okay, that's it. Very simple. All right, now, this is for R chart. Okay, how we calculate X bar chart. Okay, actually, the equation here will be a little bit similar, but of course, it's different, but it's a little bit similar. Okay, now, still, let's first look at the first sample. Okay. Okay, in this specific sample, we have 4 observations. Okay, how we get the sample mean of this sample? How we get this? Very simple, right? You basically add all these 4 elements up, divide by how many? 4, because you have 4 observations. So you add all them up, divide by 4. This is corresponding sample mean. Okay, but still, okay, when we try to get UCL for X bar chart and LCL for X bar chart, you are not directly trying to get X bar. You are trying to get X double bar. Okay, you are trying to get X double bar plug into this specific equation. Okay, what is X double bar? It's the average of the sample mean. It's average of sample mean. You already get the sample mean. Okay, follow what I just did. You can get sample mean for every single sample, right? For every single sample. Then what is the average of sample mean? The average of sample mean, basically, you still add all them up. Okay, add all them up and divide by how many? 5, because you have 5 samples. You are getting the X double bar, which is showing right here, which is 0.5027. Okay, so then you plug into this specific equation for to calculate UCL and LCL for X bar chart, right? Showing here, X double bar. Okay, what is the R bar? Remember, we already figured out R bar when we calculate, R chart. So here for X bar chart, we still need to calculate R bar. Okay, that's why here I actually I do a comparison between R chart and X bar chart, because you see R bar here is still included within X bar chart. Okay, so the process is still the same. Okay, just look through that. And how we get A2 within this specific example, still you have 4 observations within average sample. So if you look at this table that I provide to you, you look at n equals 4, you can see A2 is 0.729. 0.729. Then you plug back into this equation. All right. Right now, you already know the numerical value for every single element where you calculate no matter UCL and LCL. Then you get the UCL and LCL very quickly. Okay. So this will be the standard process that we will go through. Okay. We will calculate for no matter R chart and X bar chart. Okay. And after you get UCL, you can definitely double check UCL for R chart, LCL for R chart, okay, following, exactly the way that I just mentioned, okay, and you find out that actually the result will be like this, okay, and remember what is the control chart? Control chart is a visualization of the whole process. That's why finally, okay, in many cases, we will visualize the process that we just mentioned, okay, and you can see that here, after you calculate UCL for R chart and LCL for R chart, okay, which is corresponding to, you could clearly see 0.00479, okay, for UCL, right? Showing here UCL, okay, this is upper limit, and you can guess the LCL, which is zero, showing here, okay, showing here, and then, okay, after you guess the upper limit and lower limit, you can plot out every dot within this chart. Remember, what actually every dot is representing for within R chart. Very straightforward, right? This is representing the sample range. Okay, this one specific sample characteristic, sample range. That's why here, okay, for the first dot, actually it's represented sample range within the first sample, which is the value, show here, 0.0018, 0.0018. So that's why here you see this dot is actually representing 0.0018. Okay, so you plot every sample range within this specific chart, okay, it will be looking like this. And for this one, you see this is still in control because right now you cannot see a very clear trend during this process. And also all of the data is actually between upper control limit and lower control limit. So that's why here we say process variability is in statistical control. Okay, that's it. Now, if we go to the X bar chart, I actually already go through the mathematical detail about how we basically calculate UCL for X bar chart and LCL for X bar chart, right? So here I basically just list the expression, okay? So you will see that UCL is 0.5042 and LCL is 0.5012, okay? Now, still the same thing, okay? We do the visualization. We basically plot the upper limit 0.5042 and lower limit, which is 0.5012, okay? So this is the upper limit and this is lower limit, okay? And then what we need to do. Within the X bar chart, remember, every dot is representing what? Is representing the sample mean. It's representing the sample mean, right? So that's why here for first dot, this actually represents which value? If we go back to this table, we actually calculate this one, right? This is representing 0.5018 because this is corresponding to the first sample mean, the first sample mean. That's why here, see, this is this value shown here. So you plot out every dot, okay? And you look at the overall trend, okay? Look at this. It's actually, trying to send you some message, of course, right? You see, obviously here, you see already above the upper control limits, right? So it breaks the upper control limits such that basically it tells you that you see the process average itself is not in statistical control. It's sending you some message. You have to deal with this problem and try to fix it if you are an employee who is monitoring this whole process. Okay, so this would be a standard process how we calculate UCL and LCL for both R chart and X bar chart. Okay, now related to the X bar chart, there is actually another version of calculating UCL and both UCL and LCL related to the X bar chart, okay, which is also shown here, okay. This version is used when we know the standard deviation of the population, and also we definitely know the sample size, okay. Okay, so let's look at this. If the standard deviation is known, okay, and if we want to calculate the X bar chart, the corresponding UCL and LCL, how we calculate this? There we provide the corresponding equation. You can clearly compare this with the first version, which we show, I think, right here, okay, right here. You can clearly see that when we try to calculate both UCL and LCL, the first element showing here is still a double bar, okay? It's still a double bar. Basically means that actually for this part, we basically follow the exact same process as we just mentioned, okay? The part that will be different will be the second part. Remember, in the first version, when we try to calculate these using an LCL, all right, we use table, right, which to get A2, and also we calculate R bar, okay? But here, instead of doing that, okay, in this version, we do not do like that way. In this version, we basically calculate the corresponding Z value and also the corresponding sigma X bar. Okay, let me illustrate one by one. First of all, what is Z value? I think you guys probably already know what is Z value, right? Since all of you already took a BSTAT course, right? So Z value basically is basically the significance level, which is based on the normal distribution. And within our exam, normally I will provide you the Z value directly instead of letting you guys to calculate, yourself. Okay. So, but exactly understand what is the key sense of Z value, okay, at least. So basically it's representing the significance level with underneath, so based on the, normal distribution. What is sigma X bar? Sigma X bar is the standard deviation of the sample, okay, the standard deviation of the sample, okay. We say that when sigma is known, what's this sigma? Sigma is a standard deviation of the population, okay. So when the standard deviation of the population is known, we can further calculate the standard deviation of the sample. But it doesn't mean that these two things are exactly the same. No, there are two symbols, right? But what we use within the expression is sigma X bar instead of sigma, okay, instead of sigma. So means that if I give you some information related to sigma, you have to first calculate and translate to a sigma X bar before you use it within the equation, okay, within the equation. Now, let's look at this. This actually also should be mentioned within BSTAT course, right? Sigma X bar equals to sigma over square root of n. I will not take time to go through this equation, but this equation is very straightforward. All right. Now let's use the example to illustrate. So for example, all right, here I provide some context, but here let me translate to the mathematical expression. All right. Basically here, the context gives you all these different informations. First of all, it tells you that x double bar equals 5 minutes. The sigma, the standard deviation here, okay, of the population is 1.5 minutes, all right? And the n here is representing 6 customers. Basically, for every sample, it includes 6 customers, okay? And z value, I directly tell you, which is 1.96. Okay, if I use all this information provided by the context, how we calculate UCL for X bar chart and also LCL for X bar chart, still, okay, very simple. You first, just plug into this specific equation, right? So you first plug in 5.05 minutes for X double bar, should be here, all right? Z value is 1.96, which is representing the significance level within the normal distribution, okay? And it's finally, okay, since you know sigma, which is the standard deviation of the population, is 1.5. But remember, before you use that within the equation, you need to divide it over square root of n to get the sigma, you see, to get the sigma x bar, okay? Sometimes students may forget about, translate sigma into sigma x bar. They may directly use the sigma. No, that's not incorrect. That's not correct, all right? So you need to use sigma x bar here, okay? Here, what I show here, sigma over a square root of n, basically is representing sigma x bar, okay? So that's how we basically, why we plug in, you see, 1.5 over square root of 6 in order to get the UCL and LCL, okay? In order to get the UCL and LCL, okay? So, yeah, then we get results and still, okay, we can here, I didn't actually plot out the corresponding X bar chart, but you can plot the UCL and LCL and monitor whether this whole process is within this range or not. If it is within the range and if it's kind of normal, then yes, this is in control. But if it's out of the range, definitely this whole process is out of control. Okay, very simple way to illustrate it. Now let's move to the third chart that we will learn about, all right, within control charts part, all right, which is called p-bar chart. So as I just mentioned, all right, the key point of p-bar chart is that basically we're using p-bar chart to monitor how the fraction of defective products fluctuate in the production process. Okay, so basically what means by fraction of defective products, okay, which is very straightforward and simple, all right? For example, let's say you have 10 different products, okay? And you finally find out that 3 of them are defective products. What is a fraction of defective products? Or we say, what is the ratio of defective products? Very simple, right? You just use 3 over 10, which is 0.3. That would be the ratio or the fraction of defective products within the sample, all right? And here, we need to calculate the p-bar. Okay, I will talk about how to calculate p-bar by using basically a specific example. Okay, that'll be much easier for you to understand. And besides that, after you get the p-bar, okay, we also need to calculate z and sigma p. First of all, for z, basically, since you guys already learned about B-stat, you definitely know how to get the z within the z table. Okay, but with the exam, normally I would just directly tell you what is the z value, okay? But if you have any question, to get calculate by using z table to get the z value, feel free to let me know. All right. Another key element is basic sigma p. How to get the sigma p? The expression is shown here. Very straightforward. After you get p-bar, you directly just put p-bar value into the specific equation. All right, and you also definitely what is n, right, which is sample size. And then you can very simply get the sigma p, okay? And after you get sigma p, if you plus z sigma p, you get the UCL. If you minus z sigma p, you get the LCL. That's it, all right? Now, let's use one example to illustrate it. I will not go through the context here, okay? Please go through the context. And here, the basic information are provided within the specific example, okay? What this means. Of course, within the context, there's one very important thing that you need to know. Basically, it tells you that for every sample, the size is 2,500. right? Since every random sample of 2,500 deposits is included. Okay, keep that in mind. Now, let's get back to this table. So it tells you that actually we collect 12 different samples, all right? And within first sample, what is the corresponding, you see, wrong account numbers, or more generally, we say this is defective products, right? So 15, all right? So basically 15 out of the 2,500 deposits within the first sample is wrong, okay? Other than that, the other, deposit which would be right, all right? And with the second sample, 12 out of 2,500 is wrong. And in the third sample, 19 out of 2,500 is wrong, something like that, all right? For all of the different samples. Then how we calculate p-bar. You see, since actually sigma p is also dependent on p-bar. How we calculate p-bar? Very simple. Here I already list the corresponding equation. Okay, very straightforward. Let me help you to illustrate. First of all, we need to calculate total defectives. The total defectives would be the numerator. Okay, what is the total defective? How to calculate this? Very simple, right? Here you have 12 sample. In every sample, you exactly know the number of the defective products, right? You add all them up, which will be 147. That's why you see here, the numerator will be 147. That's it, all right? Then, since we are talking about what? The fraction of defective numbers, then what is the basement? The basement would be the total observations, all right, in all different samples. How we calculate this? Very simple, right? In every sample, you have 2,500 deposits, right? 2,500 deposits. In every sample, how many samples you have? You have 12 samples, right? So 12 times 2,500, 12 times 2,500, you get the basement, you get the overall, all of the number of the observations. Then you can directly use 147 divided by this whole number to guess the p-bar. And once you get p-bar, just plug into the specific equation to get the corresponding standard deviation of the p-bar, okay? This is not standard deviation of population, this is standard deviation related to p-bar, okay? This equation actually is following another simple distribution. We're not talking about detail about it, all right? But if you're interested, just let me know. All right, we can discuss it. And here, you can clearly see that after you get 0.0049, you plug it into this equation, you will get the corresponding sigma p, okay? Now, after you get p-bar, sigma p, and if I tell you what is the corresponding z-value, you can very easily guess the corresponding UCL and LCL, all right? So here, yeah, see, still the same thing, right? We plot out the corresponding plots, all right, the corresponding charts, and you can clearly see that LCL here and the UCL showing here, okay? And you basically plot every dot. Remember, what is the corresponding dot showing here? What is the corresponding dot showing here? Very simple. Every dot is showing the fraction of defective products within every sample, okay? So for example, this one, we use within sample one, we use 15 divided by 2,500. This value is shown here. Okay, this value shown here. You can definitely look at all this value shown here. And if you look at this pattern, first of all, you can clearly see that this pattern the variation itself is a little bit large, all right? And more severely, okay, one dot is over the UCL, which of course shows that actually this process is already out of control. You have to deal with it if you are an employee who is monitoring the whole process, okay? Another very important thing that I want to emphasize is that, okay, no matter within UCL and LCL, when we try to calculate UCL and LCL, okay, both UCL and LCL have to be at least non-negative, okay? Both UCL and LCL have to be non-negative. So if you get LCL, which is a negative one, which is negative value, okay? If you use this equation to get negative value, for example, if this LCL, okay, if you get which is, for example, negative 0.0007, okay, you need to normalize to 0, okay? This rule is valid for all charts, okay? Keep in mind, all right, no matter UCL and LCL, it has to be non-negative, okay, non-negative. If you get a negative value, you have to normalize it to 0, okay? Because UCL and LCL, if it's negative, it doesn't actually have any meaning. That's why we normalize to 0, okay? This is one thing that I want to point out. Now, let's move to the last type of charts that we will go through within the control charts, okay? C chart. Actually, the structure here will be exactly the same, although this is still monitoring another different type of the sample characteristic, okay, which is a number of defects per unit. As I said at the beginning, in some type of the products, actually it may include multiple parts, right? And you may have multiple defective parts within one specific product. So it can be 0, it can be 1, it can be 2, it can be 3, right? So if we try to monitor how the number of defects per unit fluctuate during the production process, we use C chart. And you can clearly see that, right? When we try to calculate both UCL and LCL within the C chart, this equation is also different. But if you just look at, you see the every element, all right? The every element, you can clearly see that actually this element will be very similar, right? Will be very similar as what we just mentioned for P-bar chart, all right? First of all, here we have this C bar, okay? C bar basically is the mean of the distribution. Okay, I will use the example to follow this solution. What is the mean? What is the meaning of the mean of distribution? Okay, very simple actually. All right. Now, after you get a C bar, okay, you can get the corresponding standard deviation. You can get the corresponding standard deviation. And the corresponding standard deviation is very easy to get. You just take the square root of it. Actually, this is following the which is called Poisson distribution. That's why you take the square root. This will give you the corresponding standard deviation, okay? And after you get C bar and the square root of C bar for this part, all right? You plus Z times the square root of C bar, you get UCL. You minus Z times square root of C bar, you get the LCL. That's it, okay? That's it. Now, let's use a quick example to illustrate everything showing here, okay? So the key information showing here is that when the paper production process is in control, the average is 20 defects per row. Okay, the average is 20 defects per row. Okay, so if we want to try to set up a control chart for the number of defects per row, okay, how we set it up basically means that what should be the corresponding UCL and LCL. Okay, since we already tell you that basically the average is 20 defects per row. Okay, basically per product or per service. All right, then okay, when we try to get the corresponding UCL and LCL, okay, the average number of defects per row is already representing C bar itself, okay? Because C bar is basically represent the average number of the defective products, okay? Defective parts within every product, okay? So that's why here, actually within this content, I directly tell you, okay, what is the average number of defective parts within every product, which is 20, okay? Which is 20, show it here, 20, okay? And that's why here, since you know C bar, you can clearly calculate, you see the square root of C bar, okay, the square root of C bar, which is a corresponding standard deviation, okay? And if I continue to tell you what is the Z value, or you calculate you get the Z value by searching on the Z table yourself, you can plug in all these elements, all these numbers within, you see the equation very easily, and it gets the corresponding UCL and LCL, okay? And after you get to UCL and LCL, what do you need to do? You start to monitor everything, right? That's why here, if you look at this part, all right, if you look at this part, you can see that UCL is 28.94 and LCL is basically 11.06. Then, since in part B, I already tell you that basically the number of the defective part within every row is correspondingly is 16, 21, 17, 22, and 25 for the first 5 rows, right? So you can clearly see that actually the 6th row would be having 5 defects. So you can very easily plot out every dot corresponding to every number shown here, okay? So if you directly look at this plot, the first 5 plots are kind of normal, all right? But obviously the 6th dot shown here, okay, is already breaking the LCL, okay? So of course, the process here technically is already out of control, because you see, if you look at sample 6, it's already break the LCL. But does it mean that this is bad in terms of the quality management? Remember, what we are trying to monitor within the C chart. The C chart here basically trying to monitor the number of defective parts within every single product, right? So here within the sample 6, it means that actually the number of defective products within the sample 6 is actually lower than expected. What it means? It means that actually here, as we show within the context, right? By changing the supplier, okay, actually the number of defective products, okay, within sample 6 is actually decreasing a lot. Okay, so is it a good thing or is it a bad thing? Okay, from the manager insight perspective, it's actually a good thing. So that's why here my conclusion is that yes, this is out of control, because you see the C chart, they show very significant indicator that basically in sample sets they already breaks the basically LCL, but it breaks the LCL, which is a lower limit, means that after you change the supplier, the number of defective parts within products, all right, are actually decreasing significantly. So that would be a good signal actually. So that's why here, this is out of control technically, but actually by changing a new supplier, it's a good indicator. Okay, so that will be the conclusion, managerial conclusion related to this specific example. Okay.